Have you ever seen the rays of the sun in open space? No, we cannot see them, right? But if the same sunlight passes through a dense area filled with trees, we can still see the sun rays, or we can see the path of the light. Have you ever wondered why this is so? Let us understand this today. You already know that a thicker layer of gas surrounds the earth. Yes, it's the atmosphere. The atmosphere consists of 78% nitrogen and 21% oxygen, and the remaining 1% are the gases like helium, argon, krypton, etc. Not only this, but atmosphere also contains a certain amount of water, both in the form of steam and droplets, as well as smoke particles, suspended dust particles, etc. Since these particles are larger and are evenly spread in the atmosphere, so when sunlight enters the Earth's atmosphere, the atoms and molecules of various gases in the air absorb the light. Then these atoms re-emit light in all directions. Yes, in all directions, the light is spread out. In simple words, when a small-sized particle happens to be in the path of light, the light gets deflected in different directions. This phenomena is called the scattering of light. So how can we define it? Scattering of light is the phenomena of bouncing off electromagnetic radiation by the atoms or molecules of the mediums through which they are traveling. So when light travels through a medium, it bounces off in many directions after striking the particles in the medium. Precisely, the light gets absorbed by the molecules of the medium, which later re-radiates the light in different directions. The atoms or the particles that scatter the light are called scatterers. The amount of scattered light depends on the size of particles and the wavelength of the light, right? Yes, absolutely. We will discuss them in detail in our next video. But for now, remember that shorter wavelengths scatter more due to the waviness of the line. On the other hand, longer wavelengths scatter less. This fact can be put into an equation like this. I, which is the intensity of the scattering, is equal to 1 upon lambda raised to 4. Here lambda is the wavelength of light. Here I is the scattering factor, which indicates the amount of scattering of the wave. Thus, with increasing wavelength, scattering becomes less, since they are inversely proportional here. Now we know that if something depends on wavelength, it also depends on frequency. Therefore, the scattering of light also depends on frequency of light. We can say that if frequency increases, the scattering also increases, and if frequency decreases, the scattering decreases. It's simply the inverse or reverse to the wavelength and scattering relation. Now, why this is inverse? Because wavelength and frequency are inversely related. And what about the size of the particles? Yes, it determines the color of the scattered light. Smaller particles scatter the light of shorter wavelengths like blue and violet, and larger particles scatter longer wavelengths like red and orange of the visible spectrum. Since the wavelength of blue light is lowest amongst the visible spectrum, it is scattered the most. In contrast, red has the longest wavelength and it is scattered least. So what we have seen till now is 3 factors which determine the scattering. 1. Wavelength by this equation. Second, frequency by the equation as seen, and third, size of the particle. So can we conclude that it is not the case that same scattering occurs every time? Yes, we can. We can say that though source of light may be same, but the scattering of its light may not be same. Now students, look at this image. Does this image remind you of anything? Yes, you are correct. It is the activity you performed in lower standards to test for the Tyndall effect. Am I right? Just recall that Tyndall effect is the phenomena in which the particles in a colloid, yes, the colloidal solution, scatter the beam of light that are directed at them. So again, Tyndall effect is one of the phenomena which shows scattering of light. This effect is exhibited by almost all colloidal solutions and some very fine suspension solutions as well. Therefore, it can be used to verify if a given solution is colloid or not. I mean, we can use Tyndall effect to find out whether the solution is colloid or suspension or normal solution. The intensity of scattered light depends on the size of colloidal particles. Let's quickly recall about this. When a beam of light passes through a colloid, the colloidal particles present in the solution do not allow the beam to completely pass through. The light collides with the particles and it is scattered in all the directions. This scattering makes the path of light visible. Tyndall effect was first discovered by and is obviously named after the Irish physicist John Tyndall. The diameters of the particles that cause Tyndall effect can range from 40 to 900 nanometers. So we can say that Tyndall effect is nothing but a phenomena of scattering of light. So now can you think of examples of scattering that you have noticed around yourself? I'm sure you must have. Milk is a colloid that contains globules of fat and protein, and it is a solution which shows this scattering effect. When a beam of light is directed at a glass of milk, the light is scattered and you can see its path. This phenomena is seen when a fine beam of sunlight enters a fog-filled room through a small hole. In fact, when a torch is switched on in a foggy environment, the path of light becomes visible. Here, the water droplets in the fog are responsible for the light scattering. So fog is a kind of colloid solution. Not only the path of light is visible, but also smoke or fog particles become visible due to the scattering of this light by the particles suspended in the air of the room. Now hold on students and tell me, is this an example of Tyndall effect or scattering of light? Pause the video and think about it. Yes, absolutely, it is the image showing Tyndall effect or scattering of light. Here we can see that path of light becomes visible in canopy of a dense forest. When sunlight enters the canopy of a dense forest, tiny water droplets in the mist scatter light. Due to scattering of light, the particles suspended in the atmosphere shine, and thus the path of light becomes visible to the observer. So students, in this video we have seen about scattering of light. In the next video, we will see in detail about factors that affect the scattering of light. So see you in the next video.